Have you ever wondered how scientists actually detect invisible explosive residue on a piece of luggage at the airport? Or, how they test athletes for trace amounts of performance-enhancing drugs? Well, the answer comes down to solving the ultimate scientific challenge. How do you actually weigh a single invisible molecule? Welcome to this explainer. Today, we're going to unpack the completely fascinating machinery that makes this exact thing possible.
Okay, let's dive right into this. We're focusing on the basic theory and instrumentation of the mass spectrometer. And let me tell you, this isn't just some boring machine sitting in a lab. It's an incredible analytical journey. We're going to take what I like to call the journey of a molecule, following a microscopic sample from the exact moment it enters the instrument all the way to the moment it's transformed into readable digital data on a computer screen. To do this, we'll physically trace our sample through 5 main stops. First, the big picture. Second, getting in and getting charged. Third, the sorting hat. Fourth, catching the signal. And finally, the output.
So let's kick things off with part 1, the big picture, a century of Nobel Prizes.
Now, you might be wondering, why does this matter? Well, understanding this machine literally unlocks the foundational secrets of modern biotechnology, forensics, and environmental science. It's absolutely the gold standard for figuring out exactly what a substance is made of. And it's got quite the pedigree, too. The foundational physics actually date all the way back to the late 1890s. We're talking J.J. Thomson determining the mass-to-charge ratio of the electron, and Wilhelm Wien studying the magnetic deflection of charged rays. Both of those guys won Nobel Prizes for that work. In fact, to date, no fewer than 5 Nobel Prizes have been awarded for discoveries directly related to mass spectrometry. The earliest version of the instrument as we'd recognize it today, that was built by A.J. Dempster way back in 1918.
So, how does this century-old science actually operate inside a modern, cutting-edge lab? Well, here is the literal blueprint for our explainer today. These are the 5 fundamental components that are going to take us from a physical sample straight down to digital data. We've got the sample inlet, the ion source, the mass analyzer, the detector, and the data system.
Moving right along to step 2 on our journey, getting in and getting charged, the vacuum.
Okay, so before we can even think about weighing a molecule, we have to get our sample out of the normal laboratory atmosphere and into the high vacuum environment inside the machine. It's got to be introduced into the ion source as a steady stream of vaporized molecules. Now, if the sample is already a gas, great, we're good to go. But if it's a liquid or a non-volatile solid, we have to use specific inlet systems to get it in there. We might use a direct heated probe for less volatile materials, or we can couple the mass spectrometer directly to a chromatograph. In gas or liquid chromatography, you'll hear those called GC or LCMS. Complex mixtures are separated out first and then introduced into the mass spectrometer just one single component at a time. Once those vaporized molecules are finally inside, they enter the ionization chamber. This is where we have to give them an electrical charge. Now, what's really interesting about this setup is that electron beam right in the center of the chamber. In a process called electron ionization, or EI, a heated filament basically shoots a 70 electron-volt beam of high-energy electrons directly at our stream of sample molecules. It's honestly a lot like playing molecular billiard balls. That intense collision physically strips an electron right off the sample molecule, creating a positively charged ion. We call this a radical cation, which is really just a fancy scientific way of saying, hey, this is a molecule that is now missing one electron. From there, a repeller plate actually pushes these newly formed positive ions toward a set of accelerating plates, and those plates shoot them out into the machine as a rapid, focused beam.
Now, as you can probably imagine, blasting a molecule with 70 electron volts of energy is considered a hard ionization method. It imparts so much excess kinetic energy that it's basically molecular trauma. It violently fragments the molecule into a bunch of smaller pieces. But what if we want to keep the molecule intact? Well, for that, we use a soft method called chemical ionization, or CI. Instead of hitting the sample directly with those high-energy electrons, we use a vast excess of a reagent gas, something like isobutane. The reagent gas gets ionized first, and then it gently transfers a proton to our sample molecule through soft collisions, keeping the whole thing largely in one piece.
And for those truly massive, non-volatile biological molecules, we rely on some absolutely incredible sampling techniques like electrospray ionization, or ESI. In ESI, a liquid sample is sprayed through a high-voltage capillary, eventually leaving naked, highly charged ions suspended right in the gas phase. Because ESI can actually add multiple protons to a single molecule, it allows us to analyze massive proteins. Just take a look at the chicken egg white lysosome right here, casually carrying 10, 11, or even 20 positive charges. We are literally going from tiny gaseous molecules to massive biological structures in a flash. This specific technique was a total game changer. It literally opened up the modern world of biotechnology and protein sequencing.
All right, that brings us to Section 3, the sorting hat mass analyzers.
Now that our molecules are charged up and accelerating, we are entering the absolute heart of the machine. This is where electromagnetic fields separate our newly formed ions based strictly on their mass-to-charge ratio. Think of mass analyzers like highly sophisticated sorting systems for coins, but instead of sorting a quarter from a dime based on physical size, they're sorting by mass and electrical charge. There are a few different types of these analyzers out there depending on the specific application, including the magnetic sector, the quadrupole ion trap, and time-of-flight mass analyzers.
So how do they sort? Well, in a magnetic sector analyzer, our rapid beam of ions is shot directly between the poles of a strong magnet. Physics dictates that a charged particle passing through a magnetic field is going to follow a curved flight path. But here's the catch. The exact radius of that curve depends directly on the ion's mass-to-charge ratio. Lighter ions are going to bend sharply, while the heavier ones just plow right through with a much wider arc. By continuously varying the strength of that magnetic field, we can precisely control which specific mass-to-charge ion perfectly negotiates the curved tube to reach the detector at any given millisecond. It's incredibly precise.
But other analyzers use entirely different physics. Take a quadrupole analyzer, for example. Here, ions pass through 4 parallel metal rods that generate oscillating radio frequency and direct current fields. Only ions of a very specific mass-to-charge ratio can maintain a stable, corkscrew-like trajectory through those rods. All the rest, they spiral out of control and crash. Then you have the time of flight, or TOF analyzer. This is basically a molecular drag race. It gives all the ions the exact same kinetic energy pulse right at the start line and simply times how fast they travel down a long vacuum tube. The lighter ions fly faster and hit the finish line first. Simple, but brilliantly effective.
And that finish line brings us to Section 4, catching the signal, the detector.
Whichever sorting hat we happen to use, the surviving ions eventually cross into the detector region. Here, we face a new challenge. We've got to translate a tiny physical ion impact into a readable electrical current. To really grasp why this step is absolutely critical, just consider this number. Let's say you inject a tiny 1 microliter sample into a GCMS. By the time it gets split, vaporized, and ionized, you might only have about 3.6 billion ions left. Now sure, that sounds like a lot, but in a scanning spectrometer, the vast majority of those ions are deliberately discarded into the walls of the analyzer. An ion of a specific mass might only actually make it through the analyzer 1 time out of 300. We are dealing with an extraordinarily small number of actual physical impacts at the finish line, meaning we need some pretty incredible sensitivity. And this brilliantly illustrates exactly why we need something called an electron multiplier. When that rare single ion finally strikes the surface of the detector, it physically ejects a couple of secondary electrons. Those new electrons are then accelerated by a voltage potential into the next surface, which knocks loose even more electrons. This creates a massive cascading avalanche of electrons. It amplifies the tiny physical impact of just one single ion into a robust, measurable electrical current that a computer can actually read.
Which leads us to our 5th and final stop, the output data processing. We've made it. We have successfully gone from a physical sample to a cascading electrical signal. Now the data system translates that electrical current into a visual mass spectrum graph. If you take a look at the x-axis along the bottom there, that shows the mass-to-charge ratio. Essentially, that's just a mass of the ion, assuming its charge is +1. Then over on the y-axis, we have the relative ion abundance. That simply tells us how many of those specific ions actually survived the journey and struck the detector.
As you're looking at this, you'll immediately notice that one peak is way taller than all the rest. We call this the base peak. It represents the single most abundant ion that was formed back in the ionization chamber. The computer essentially normalizes the entire spectrum by setting this base peak to 100% relative abundance. From then on, every single other peak on the graph is just measured as a percentage of that tallest peak.
So, what does this all mean for our initial question? Well, the crucial point here is finding the molecular ion peak, which is usually marked as M+. This particular peak represents the molecule that lost an electron right at the beginning, but miraculously managed to travel the entire length of the machine without breaking apart into fragments. Assuming we are looking at the heaviest isotopes, finding this specific peak way over on the far right of the spectrum finally gives us the exact molecular weight of our original invisible molecule. We did it!
And there you have it. We vaporized a physical sample, knocked an electron off to charge it, sorted it through powerful electromagnetic fields, multiplied its tiny signal into a giant avalanche, and charted its exact mass. It's just wild to think about. This century-old analytical technique is nothing short of miraculous. But you know what? Weighing the intact molecule is just the beginning of the story. The real detective work happens when we look at how these molecules break apart. So, how will analyzing those tiny fragments unlock the next big breakthrough in biotechnology or solve tomorrow's most complex forensic mysteries? Well, we're going to dive into the incredible puzzle of fragmentation analysis in Part 2. Thanks so much for exploring with us today.